If you remember what a linear combination is a scalar times a vector. And if you add up all those scalar times vector linear combinations, your result is going to be another vector, and any of those vectors would result in the span of this thing. And it turns out that if you take the span of S, the span of those vectors, and the span of those vectors happen to be able to reach every single point in Rn, then that is called a spanning set. Is all that making sense so far? No. If you take all these vectors, v1 through vk, and it turns out that the span of that is everything, everything in your Rn, whether you're in R2 or R3, then that is called a spanning set. All right, so let's talk about spanning sets in a little while. Let's first talk about what span means. What does it mean to span something? So with that, I got a visual, and I've been working on this Mathematica program file. Would be this one first, where I would define a vector, and then I would define two vectors, and I would draw two vectors and see what the span is. So these are my two vectors. Now let me just take as an example the vector 1, 1 and the vector 2, 2. And let's imagine what the span of those two vectors would be. What do you think the span of those two vectors would be? Do you understand what span is? The span of those two vectors would be a line. Now, were you guys, does that make sense? No? Okay. It would actually be a line, and what that means is that each point of that line can be represented as a vector, and the only linear combination you can get would be every single point on that line. So let's actually write that up before I do that example, before we get the visual. So as an example, suppose your v1 is equal to the vector 1, 1, and your v2 is the vector 2, 2. And you ask yourselves what the span of this is. The span of this would be any linear combination. So if you get a w is equal to some alpha 1. We use alpha for scalars, right? Remember? I forgot. Alpha 1 times v1 plus alpha 2 times v2. And it doesn't matter what alpha is. You can put any alpha you want here, and then you try to describe all these vectors that are possible in this scenario. So if you have these two vectors, you got alpha 1, 1, 1 plus alpha 2, 2, 2. This looks like it's alpha 1 times 3. Is that right? No. Alpha 1 plus alpha 2. 2 alpha 2. Alpha 1 plus 2 alpha 2. So what do you notice about this vector over here? What do you mean by a line? Not quite. It's. What do you notice about this vector over here? It's what? The x and the y components are the same, right? So it doesn't matter what alpha 1 and alpha 2 are. The x and the y components of this vector will always be the same. So it looks like here x component and y component are the same. So it looks like this is going to span all those vectors whose x and y components are the same. This will span a space. I'll put space in quotes because it's really just a one-dimensional space, which is a line. A space whose x, I'll just say a space where x equals y. Okay? So the span of this, we can actually visualize it because it's in 2 dimensions. The span is just a line. Since both vectors are pointing in the same direction, or even if they're pointing in opposite direction, they're collinear, that span of that is just going to be scalar multiples of these things, which is just adding the same things over and over again. So to see if we can get a visual of this. So these two vectors, they're right on top of each other. I tried to make one of them red. I suppose if I switch the order. These vectors are all both vectors from the origin. So if I wanted to make a span of that, a span of this would be any linear combination and then add it to each other would just all fall in the same line. Do you see how that would just all fall in the same line? No? If I take a linear combination, if I take a vector here, here's a good thing to think about. What if I add a point? The vectors, the point. So I'm going to add the point 2, 0 on this picture. That's my point 2, 0. Here's a question. Can I add those two vectors with scalars? Can I scale and add those two vectors and eventually get to that point? Is my question. What do you think? So the question is, what was my point again? 2, 0? 2, 0 in the span of V1 and V2. So is my vector in a span. Can I get to that point by just adding and scalar multiplying those vectors? So if we do that, we basically have the same equation over here. Alpha 1 V1 plus alpha 2 V2. Can I set that to equal to 2, 0? No. Well, let's see. What I would have is I would have alpha 1 plus 2 alpha 2, alpha 1 plus 2 alpha 2. I got that over here, right, is equal to 0. So I have a system of linear equations. If I break this, if I take the matrix stuff out and then set the top equation equal to 2, set the bottom equation is equal to 0, I have a system of linear equations. 1, 2, 2, 1, 2, 0, augmented. And then if I try the row reducing, what am I going to get? I'm going to get 1, 2, 2, and 0, 0, 2. So I don't get a solution here. I can't. So that's from the matrix way of doing it. You can say that 2, 0 is not in the span of this. Yeah, so you can basically create this just by putting the column vectors together. Remember that theorem that we saw earlier or last time? There was something about the column vectors to see if it's linearly independent. Okay. So the thing is, there's no way we can get to that point if all we have are these two vectors. Does that make sense? All right. Okay. All right. So this would be an inconsistent system. Let's write that. Usually inconsistent isn't the best way to start off with, but here we are. We're doing an inconsistent system. Okay. So let's change one of these vectors. Let me change, I don't know, which one should we change? Let's change 1, 1 to -1, 0. So now my vectors look like this. Actually, instead of, I want to just stay with smaller numbers. So instead of 2, 2, I'm going to say 1, 1. So 1, 1, and 1, 0. Now, these two vectors, just by looking at the picture, clearly they're not on the same line, right? So they're in different lines. So I can say that one is not linearly independent from the other, which means one is not a scalar multiple of the other. Okay, they're not scalar multiples. So the question is, can I scalar multiply these vectors and get to that point? Okay, so now let's start up another page with a new example. What were my vectors again? (1, 1) and (-1, 0). So these are my two vectors. Let's figure out what the span of these two vectors is. The span of these two vectors. So if I were to ask you what the span of these two vectors are, what do you think you can say? Let's look at it from the graphical point of view again. A span, remember, is taking the scalar multiple of each vector, and then you get to add scalar multiples of these vectors. So imagine these vectors being scaled, right? So if I scale this first one, I would have like a line going through this red point. And then imagine if I add the blue vector to that line, then what would I have? Another line parallel to it, right? That's been shifted a little bit. So if I do a bunch of those, what am I going to get? Yeah. You would end up spanning the entire plane. Okay? So let's see if I can do this slowly. That's not what I wanted. Line goes from... This is going to ruin everything? This is going to ruin everything. All right. Well, something's going on. I can't do it quick, so I'm going to so the span, if I imagine taking the red vector and stretching it, because the scalar multiplying both ways, I would get a line. If I add the blue vector to that line, I would get multiple lines going parallel to that line. Now imagine the blue vector. If I take that blue vector and I stretch it both ways, then I get another line. And if I add the red vector to it, I'm going to get another set of lines that are parallel to that. So the picture should look like this. So this is going to be a grid that you would have where each of these grids, each of these places where they meet would be a whole number scalar multiple of something. Does that make sense? So now that I'm looking at the point, I don't think that point's a good point. But in any case, if I were to go on forever here, I would end up spanning the whole plane. Okay, going both in the V1 and the V2 directions. Yeah.
You're talking about vector addition.
Vector addition with scalar multiplication. Yes.
I guess I'm forgetting like chapter 1. I thought like vector addition would be a diagonal between.
Yeah. So if I were to add that, the vector addition would. If I were just to add.
I don't see how they're parallel.
What?
I guess I don't see how they're parallel.
Well, the vector addition gives you like a parallelogram, right? And so these are essentially those parallelograms where I'm adding, I have 1 times V1, 2 times V2, 3 times V3, etc.
I thought vector addition touches the 2 tails. For the 2 heads or whatever, the 1 arrow points.
Yeah.
And that doesn't strike me as parallel to either of the lines.
Which? So let's see.
I guess it's all off, but it doesn't matter.
So let me move the point to 0, 1. So imagine the vector, the red vector and the blue vector. If I were just to add the red vector and the blue vector, I would get this point. Now you don't see the vector there, but you can imagine the vector going from 0 to that point. Okay?
Right. Well, what would be the operation that would span 1, 1 and negative 1, 0?
Well, if you were to add that,
Right.
this is, you would get this point. Let's see if I can make a quick vector out of that. Let me add it here. So I would go from the origin to A plus B.
I mean, I see that. Right? But I mean, from 1, 1 to negative 1, 0. Exactly. Okay. Right. Okay.
Is there?
I got it.
Okay, well, in any case, this is a little small, but let's see if we can deal with this. Yeah, we'll do that in a minute. So I have my vector 1, 1, and my blue vector is negative 1, 0. And I have my point here at 0, comma 1. So the question here is alpha 1 times the vector 1, 1 plus alpha 2 times the vectors negative 1, 0. Is there any way I can get to this vector 0, 1? Well, we could do the matrix to solve for this, but just by inspection, can you just look at it, either the drawing or the equation? Can you look at it and give me a value for alpha 1? What? If I put 1 in for alpha 1 and 1 in for alpha 2, this should give me that point, right? So 1 in for alpha 1 would give me 1, 1. Negative 1, 0. And this is going to give me a 0, comma 1. So it turns out that I can get to that point from those two things, from those two vectors. Yeah? What? No. I want to actually get to that point. All right. Let's pick another point on the plane. So this looks like it'll span the whole plane. Just by looking at the picture, it looks like it'll span the whole plane. But let's find another point. Oh no, it's shrunk. Let's find another point. So let's look at this picture and let's find another point. Like maybe we can even do fractions if you want. So pick a point in some quadrant. What quadrant should we go in? What? We're going to first quadrant. Okay. So point, let's pick something like 5 or something. 5 comma 3. So we're over there. So can we get to that point by just adding and subtracting and scalar multiplying the red and green, the red and blue vectors? I'm going to take out that orange vector. Can we get there? What should we multiply? Now I have to know which is which now. A is the red vector. What should we multiply A by? 3. And what should we multiply the second vector by, B vector? What? -2? Let's see if we can get there. Oops, I need to draw after the grid the trace. Okay, so it looks like we got there. We multiplied the red vector by 3, that stretched it, and then we multiplied the blue vector by -2, that turned it the other way and stretched it by 2. So we're able to get there. That path kind of looks a little weird. All right. Is this making sense? Is it visually making sense? All right, should we change the vector? Let's change the vector again. Should we put fractions and decimals and stuff? Make it all weird? 0.5, comma 1. And instead of 1 comma 0, 1 comma -1 comma 1. And should we keep that random point over here? Pick another point. Pick another point. Five root 2? Pi? Wow, we're getting challenging, huh? No, we can't do root I. So pi root 2 is somewhere over here that looks like this. So our task is to try to find A and B, or A1 and B, alpha 1 and alpha 2, so that we can stretch this and then make it go, in several directions. So just by looking at this, would you be able to guess approximately how would you stretch your A? What? By 2? So let's stretch our A by 2. And what would you do to B? What would you do to this blue vector if you're going to move your A vector up that way? Two-thirds? Minus 1 and 2/3? What's 1 and 2/3? 1.6 or something? All right, let's see if we can get there. So what do we need to fix? The red vector. What do we need to? We had 2 there last time. 2 wasn't enough. What should we put? 3? So that one's fairly close, right?
So is your alpha's always based on your origin?
The alpha would just take that vector and it would stretch it. from the origin it would stretch it, but then you're going to translate it anyways to do your addition. So that's why the vectors look like this. So I thought about making this kind of interesting and kind of like a game. Negative 5 to 5. Let's see if this will work. So the question is, can you move your values to get to that point? And then you can try to identify what your values are. So if we move this by about 3, and if we move this by about -2 or -1.5, we can kind of get there. Pretty cool, huh? So this one, for something like this, in that problem that we just did, you'll probably need a computer or calculator to figure this out, especially since we got this weird point. What was the point again? Pi root 2. So given those values, the question is, can we find alpha 1 and alpha 2? What was the second vector? -1, 0. So that this is going to equal a pi root 2. That's basically what we did. And we got alpha 1 to be, what was alpha 1 to be approximately? Be -3 or something? Or +3? 3.0104. And then we got alpha 2 to be approximately -1.1 and 1.56. Right? So what happens is that if you take this and take the system and write it as an augmented matrix, 1, -1, pi, 1, 0, square root of 2, and do the row reduction, you can find the exact value.
The numbers are wrong. 3.04 times 1 doesn't really do that. Those are square root of 2.
Say it again?
If you just solve the bottom line of that matrix,
Oh, yeah.
it doesn't really work. So I think maybe your vectors are wrong.
Oh, I put 0.5. Shoot. Yeah, I changed my vectors. Sorry. 0.51, -1, 1. Thank you. So 0.51, -1, 1. Yeah, I changed my vectors from this. Yeah. So the point is that we should be able to find the exact value. So your matrix would look like this, right? And I was hoping it was the first one, because the first one's easy enough to do the row reduction. Here it's a little bit more difficult. I suppose we can do it. Should we do it? Let's do it. So I'm going to switch the order because that's a valid elementary row operation. And then I'm going to take the first row and then multiply it by negative a half and add it to the second row. So negative a half, negative 1.5. And this one would be negative root 2 over 2 plus pi. Now I can solve for it here, or if I want the fully reduced row echelon form, I would multiply this to get rid of to make this into a 1 and then add it to the first one, right? So let's go ahead and do that row reduction thing. Reduced row echelon. So I need to divide by negative 1.5. So this is negative root 2 over 2 plus pi divided by negative 1.5. So I have my second one. I have my alpha 2 value, and then if I just get rid of that 1 over here, I would need to just subtract, right? So this would be square root of 2 minus this whole big mess, negative root 2 over 2 plus pi divided by negative 1.5. So if you work out these two values, you should get something that's fairly close to about 3.04 and negative 1.56. Okay? Boy, just wasting a lot of time on this. Questions? Yeah.
So after we get to there, what do we put in for alpha 1 and alpha 2?
Well, this is supposed to be your coefficient for alpha 1. So from here, looks like alpha 1 is going to equal to this square root of 2 minus this big mess. So this is saying 1 times alpha 1 is equal to this, and 0 times alpha 1 plus 1 times alpha 2 is equal to this. Okay? Yeah, if you punch that into your calculator, like I say, you should get something that's about 0.3 and negative 1.5. Okay? So you guys are just going to trust me and that's going to work? All right. Okay, let's go to 3D and see if we can get a feel for this. 3D gets a little bit more interesting. So if you're in R3, and let's say you have two vectors, and you had two vectors that were not pointing in the same direction. Because if you had two vectors that are pointing in the same direction, then your span is just going to be a line. But just if you imagine in 3D and you have two vectors that are not pointing in the same direction, and the span would be what? Span would be a plane, right? Can you tell me a little bit more about this plane, something interesting about this particular plane that's spanned by a couple of vectors? Can you tell me something a little bit more about the plane that's spanned by two vectors? Well, how about let's do it like this. What if these two vectors were actually pointing in the same direction? then it's a line, right? Can you tell me something interesting about those two vectors, the span of those two vectors? Or can you tell me something interesting about that line that's being spanned by those two vectors? No, it's in R3, but it's only spanning a line, so it's only a one-dimensional thing. No. Okay, I guess to try to lead it a little bit more, is there a special point that it passes? The origin. That's what I was trying to get at. The span of vectors, whether it be one vector, two vectors, or three vectors, is always going to pass through the origin. Okay, so that's going to be a special property for what we call vector spaces. So anyways, if we had two vectors that were not collinear in 3 dimensions, then those two vectors will span a whole plane. And that plane would be a plane passing through the origin. Does that part make sense? Now, if I had a point that's on the plane, I can get to that, right? But if I had a point that was not on the plane, then I can't get there. Does that make sense? So that idea, I got a visual for that idea. So this is the same setup, except now it's in 3 dimensions. And oh, I didn't separate it. Let's take out the trace. So if I have a span of 2 vectors, then that span of those 2 vectors will span a plane. And then if you have a point on the plane, then you can eventually get there. If your point is not on the plane, then you're not going to be able to get there. Right? Let's take that box out. So with 3 dimensions, it gets a little trickier because the plane that you're spanning, you're not just stuck in 2 dimensions. The plane you're spanning is 2-dimensional, and then if the point is not on that plane, then it's not part of the span. So what if I had a third vector? If I just had any random third vector, would I be able to span the whole space? No? If I had a third vector, would I be able to span the whole space? So my vectors are 1, 1, 1, 1, negative 2, 0. So whatever I want. So I have 2 vectors. These things span a plane. Now if I add a third vector, let me see. What if I add 2, comma, negative 1, comma 1? Then am I going to span the whole space? Yeah, yeah, or maybe. I see some no's. Why not? Because if this vector was on the same plane, then you're still not going to be able to span the whole space. Right? So so I put this vector up here, and given this vector, would I be able to span the whole space? No. Okay? If I choose another vector, can somebody give me a vector that would put together with the first 2 be able to span the whole space? I need something specific. No, that won't work. 2, 0, 1. If I had 2, 0, 1, along with these two vectors, would I be able to span the whole space? Yeah. How would you know that? Because if it's not on the plane, then you have a third vector. You have two vectors that are on the plane. And if you had a third vector that wasn't on the plane, then I can get to anywhere else on the plane by doing a linear combination of all those three vectors. Does that make sense? No?
I don't see how, I guess how does the green lose it? Is it just the rule?
Well, I mean, let's assume that this is the origin, and let's call this V1 and V2. So V1 and V2 are over here that span the whole plane. And so this green vector, I guess that was a bad choice in color selection. This vector 1, negative 1, 1, or 2, negative 1, 1 happens to be a vector that is also on that plane. So this vector 2, negative 1, 1 is on the plane. And so because that's on the plane, that third vector doesn't give me a three-dimensional span. It's still a two-dimensional span between V1, V2, and this orange vector. Because if I had a point that's not on the plane, I can't get to that point with these three vectors. I can add, subtract, scalar multiply these three vectors, but I still won't be able to get out of the plane because all three of them are stuck on the plane. Oh, why? Because the way I chose this vector, I just added these two. And then, so because that addition, I'm stuck on the plane.
It was a product of you having added U1
Right.
and 201 you just kind of made up.
Somebody made it up.
So it just can't be because it's not the two added together.
Right. So this other vector, this new vector here, this new vector is not on the plane, and so given any point in space, I should be able to get to that by a scalar multiple of these, this new vector and then the original two vectors. Okay?
If you were to pick a random point on the plane, then you can get to it with scalar multiplication.
Yeah, so if I pick a random point on the plane, then I can use only these two vectors, and I won't need this third vector to get there.
But then any point not on the plane, you just kind of see it as a plane, the entire space, and then just made three-dimensional, so any point kind of anywhere.
Right. So if you imagine seeing a picture like this, where you have two vectors over here, you can get, the only way you can get out of that plane is that if you had a third vector that took you out.
Any vector that took you out would get there.
Yeah, because even if it's pointing down, you can just multiply by negative 1 and it'll point the other way. Okay? All right, so we still haven't formally defined linear independence, so we got some catching up to do. And you have homework that's section 2.3 that's supposed to be due on Sunday, right? And I think 2.4 was also, but I'll postpone 2.4 till later. I think we're still going to have a test on Wednesday next week. So we'll finish up linear independence on Monday and talk a little bit about some of the applications. Colin?
Would you be willing to put up practice tests similar to
I'll try to get that over the weekend. Yeah. All right. See you guys.